Good day and welcome to the HydraForce YouTube channel. I'm Jim Pytel and I'm here at the invitation of HydraForce to discuss applications of the HydraForce HTD 10-40 hydraulic torque divider cartridge valve. Our objective is to examine how the HydraForce HTD 10-40 hydraulic torque divider can be used to solve some of the problems commonly encountered when two or more hydraulic motors are placed in series with one another where there exists some form of mechanical linkage between the two motors. The classic scenario being a hydrostatic drive during cornering where the outside wheel must spin faster and the inside wheel slower. We'll show how the HydraForce HTD 10-40 hydraulic torque divider can be used in place of inefficient flow dividers and expensive solutions making use of feedback by treating these scenarios not as flow control issues, but rather as a pressure control solution. I'm here at the invitation of HydraForce because my background includes regularly producing free online electromechanical technical training at my own YouTube channel. My intention is to one day offer a complete suite of free online instructional videos for students or industrial users seeking instruction in technical topics. The rising popularity of the hydraulics and electrical control of hydraulic systems playlist, available at my YouTube channel, brought me to the attention of one of HydraForce's application engineers, Travis Schmidt, and he invited me to take a look at their new product, the HydraForce HTD 10-40 hydraulic torque divider. My first thought upon reviewing the material Travis sent to me was, this is cool. I think you'll come to the same conclusion after this short presentation. I've got an appreciation for simple solutions to seemingly multi-dimensional problems, and the HydraForce HTD 10-40 hydraulic torque divider is one such solution. This presentation operates under the presumption that the viewer has more than a passing familiarity with basic hydraulics and has working knowledge of hydraulic motors, directional control valves, pressure control valves, flow control, and series and parallel hydraulic circuits. If you lack this level of familiarity, by all means, feel free to visit the Hydraulics and Electrical Control of Hydraulic Systems playlist and bring yourself up to speed regarding this basic content. My intention during this presentation is to show how applications of these basic hydraulic principles explain some of the problems commonly encountered with hydraulic motors in series, such as hydrostatic drives during cornering, and how the HydraForce HTD 10-40 hydraulic torque divider can be used to solve these issues. Let us begin. There are essentially two ways of creating a multi-actuator system. Series circuits place multiple actuators functionally in line or in series with one another, where one actuator's outflow is another's inflow. In contrast, parallel circuits place multiple actuators functionally side by side or in parallel with one another, where inflow and outflow paths split between the actuators. These functional arrangements bring with them important characteristics. Series circuits, because one actuator's outflow is another's inflow, are characterized by nearly simultaneous movement of both actuators. The pressure drop of each actuator in a series arrangement is additive, therefore the first actuator experiences back pressure from the second. This additive arrangement can also cause the actuators to experience higher reference pressures, which can affect pressure seals and drain outflow. Parallel circuits, because of the shared inflow and outflow paths, are characterized by pressurized flow being routed to the actuator with the least pressure requirement. In parallel circuits, the flow is additive, meaning the total flow is the sum of flow through each actuator. Allow me to demonstrate. Let's consider series circuits first. In a perfect world, this series arrangement of two bidirectional hydraulic motors driven by a bidirectional pump would produce perfectly synchronized operation. I've obviously stripped this circuit down to its barest fundamental components to keep things simple. When the bidirectional pump runs in the forward direction, it would produce flow traveling into motor A's inlet, out of motor A's outlet, straight into motor B's inlet, out of motor B outlet, and back to the pump. Given motor A and motor B are assumed to be equally loaded, pressure drop across both motors would be equal. Additionally, given flow rate is not diverted at any point in this series circuit, it can be said that flow rate entering motor A is the same as the flow rate entering motor B. Given flow rate is proportional to actuator speed, and given flow rate is the same through both motors, it would be expected that both motor A and motor B would turn with the same torque and rotational speed. If these bidirectional hydraulic motors happen to represent the drive wheels of a hydraulically driven two-wheel drive vehicle, the vehicle would theoretically tool along at a constant speed in a perfectly straight line. The real world, however, in stark contrast to our imagined perfect world, is known to contain buildings, trees, machines, and coworkers that would prefer not being run over. In short, The real world necessitates an operator watch the road in front of them and turn the vehicle on a regular basis to avoid obstacles. The fundamental flaw in our simple series circuit is that when cornering, the two wheels are placed on two different track lengths that must be negotiated in the same amount of time. Consider a 90-degree turn with an inside radius of, let's say, 30 feet being negotiated by an 8-foot wide vehicle. The radius of the quarter turn described by the inner wheel would be 30 feet, and the quarter turn itself would represent a path of a quarter of the complete perimeter, or approximately 47 feet. The radius of the quarter turn described by the outer wheel of this 8-foot wide vehicle, however, would be 38 feet, and the outer quarter turn would represent a path of approximately 60 feet. Can you see the problem real-world cornering applications bring to this simple series circuit? Given flow rate is constant through this series circuit, and flow rate is proportional to rotational speed, the inner and outer wheel are turning at the same speed, yet are being asked to negotiate two different length paths in the same amount of time. What this ordinarily translates into is one of two undesirable occurrences. One, the outer wheel being dragged, scuffed, or smeared along the ground, a sure deal breaker for traction-critical applications, or applications in which the wheels must be driven across an easily damaged surface, like a golf course. Or two, the outer wheel, instead of driving the vehicle around the path, is instead driven by the cornering vehicle. When this happens, the driven motor essentially becomes a pump, exceeding the available flow rate. The resulting extreme drop in inlet pressure at the driven motor causes cavitation. Cavitation damages hydraulic components and is generally to be avoided. Even in the most ideal circumstances, in which motors in series with some form of mechanical linkage between them operate at the same rotational speed, problems can still occur. The upstream motor, if it experienced any leakage through the case drain, would effectively remove that amount of flow from the series path. Consider two hydraulic motors in series, linearly driving a carriage forward and back. If the pump provided 10 gallons per minute of flow to the series circuit, and the upstream motor leaked 0.5 gallons per minute, only 9.5 gallons per minute is available to the downstream motor. Given the mechanical linkage between the two motors, the downstream motor with the decreased flow rate would potentially suffer the effects of cavitation because it would be driven by the upstream motor with the increased flow rate. A quick and inexpensive, i.e. extremely poor solution to these types of problems is the addition of a make-up check valve. Let's examine such a modification to a hydrostatically driven vehicle making use of two hydraulic motors in series. In the ideal scenario in which the vehicle is driven in a perfectly straight line, the make-up check valve remains closed and both motors rotate with the same torque and rotational speed. If, however, the vehicle turns, the outside wheel is driven at a rotational speed faster than that ordinarily enabled by the given flow rate. The induced suction at the inlet of the outside motor opens the make-up check valve, thereby preventing cavitation. While this quick and inexpensive modification does prevent cavitation, the fundamental drawback is that when the make-up check valve opens, this places the inlet port of the outside motor at suction and all pressure is dropped across the inside motor. In summary, the inside cornering wheel is doing all the work, and the outside cornering wheel is along for the ride. Such an unequal distribution of work can eventually wear out an actuator prematurely. Before we move on to discuss parallel circuit configurations and other means of flow control, I want to emphasize the fundamental flaw of including the make-up check valve in this series circuit. I say again, when the make-up check valve opens, it does allow the series motor to rotate at different speeds without cavitation. However, it places the inlet port of the driven motor at suction, and as a result, that motor provides no tractive effect and simply freewheels around the corner. Take a minute to contemplate a possible solution to this problem. Wouldn't it be great if there existed some sort of magic make-up check valve that, rather than simply opening at low pressure, ensured that both motors remained equally loaded despite differing flow rates between them? Think on this for a moment. Moving on. Let's now consider another type of basic hydraulic circuit, notably a parallel configuration. A parallel circuit places multiple actuators functionally side by side or in parallel with one another, where inflow and outflow paths split between the actuators. Because of the shared inflow and outflow paths, pressurized flow would be routed to the branch with the least pressure requirement. Consider, if you will, an ideal situation in which both wheels in a parallel configuration are perfectly equally loaded and the vehicle is traveling in a perfectly straight line. Theoretically, both motors would turn with the same torque at the same rotational speed. If, however, even the slightest imbalance occurred between the motors, flow would favor the parallel branch with the lowest pressure drop. This is a nightmare scenario for traction-critical applications. Imagine the embarrassment of operating a hydraulically driven vehicle characterized by a parallel arrangement of hydraulic drive motors when one of the two wheels hits a patch of ice, a puddle of oil, or even a spilled cup of coffee. The sudden loss of traction effectively unloads that slipping wheel, and all flow, rather than being routed to the wheel that has maintained traction, is instead routed to the wheel that has lost traction. The slipping wheel continues to spin, while the gripping wheel remains dead in the water. This undesirable scenario can be somewhat mitigated by modifying this purely parallel circuit. The most common solution is to apply a flow divider in the parallel circuit. Flow dividers are pressure-compensated flow control devices that when the pressure rises in one branch, the opposite branch is restricted such that flow through both branches remain balanced. Consider a scenario in which a hydraulically driven vehicle being driven in a straight line experiences the sudden loss of traction in one wheel. Rather than all flow being diverted to the spinning wheel and none to the gripping wheel as previously, the imbalance of pressure causes the flow divider to throttle the flow to the slipping wheel until an equilibrium is reached between it and the gripping wheel. Operated in this fashion, this would theoretically keep the gripping wheel functional. Two fundamental problems exist with this parallel circuit incorporating a flow divider. The flow divider itself is inducing a massive inefficiency in this circuit. The resulting pressure differential across the restriction increases heat and effectively wastes energy. Very often, flow dividers represent the highest parasitic loss of all components in a hydrostatic propulsion drive. 2. The flow divider doesn't solve our initial problem regarding cornering. Recall the purpose of a traditional flow divider is to divide flow equally between two unequally loaded actuators. Turning the vehicle places the inner and outer wheels on two different length tracks and necessitates the actuators rotate at different speeds. The flow divider attempts to keep flow equal, running counter to this purpose. For this reason, consider a parallel circuit making use of a flow divider incorporating a slip orifice. The slip orifice is a means of allowing a differential to occur between the two parallel paths. When cornering, an amount of flow can be bypassed from one branch to the other, thereby allowing the outside wheel to travel at a different rate. This being said, the slip orifice now represents a leakage path for a slipping wheel. For this reason, consider a parallel circuit making use of a flow divider incorporating a slip orifice that can be selectively locked out. As previously, the flow divider ensures balanced flow during regular operation, and the slip orifice is a means of allowing a differential to occur between the two parallel paths during cornering. If, however, a wheel loses traction, an operator can disable the slip passage, and the flow divider ensures the wheel maintaining a grip receives at least a portion of the available flow. If this system seems like it's overly dependent upon the good judgment and response time of a human operator, you're absolutely right. For this reason, consider a parallel circuit making use of a flow divider incorporating not a fixed slip orifice, but rather a proportional passage linked to a steering angle feedback sensor. As previously, the flow divider ensures balanced flow during regular operation. During cornering, however, the steering angle feedback sensor proportionally opens the slip orifice, thereby allowing a progressive differential to occur between the two parallel paths, necessitating different flow rates. During a mild cornering event, a small slip passage is opened. During an aggressive cornering event, a larger slip passage is opened. If, however, the wheels are held straight, the steering angle feedback sensor keeps the slip passage closed and the flow is divided equally between the two parallel paths. If this more advanced system seems like it swapped out the human involvement of our previous circuit for a larger number of more expensive components, you are also correct. Additionally, it needs to be reiterated that all the parallel circuits incorporating flow dividers are all making use of restriction-style flow control devices that seriously undermine the efficiency of our system. In summary, parallel arrangements of actuators can account for differential flow rates, however, often necessitate additional components to do so. Thus far, we've explored the fundamental differences between the two main types of actuator arrangements, series and parallel, compared and contrasted their characteristics, advantages, disadvantages, and the common means of mitigating the disadvantages of these arrangements. As we've demonstrated, purely series and purely parallel circuits aren't really workable solutions, and overcoming the undesirable characteristics of a particular arrangement often necessitate the use of additional components that may contribute to inefficiencies or expense. The closest we've thus far come to a simple, inexpensive solution is the series relationship of two hydraulic motors incorporating a make-up check valve between them. While the make-up check valve does allow the motors to operate at different speeds or different flow rates, whenever the make-up check valve opens, it places the inlet of one motor at low pressure, thereby unequally loading the pair. What most of the mitigating strategies for parallel circuits have in common is that they attempt to solve the problem using a flow control solution. HydraForce decided to take a different approach with the HTD. They saw the answer to the problem as not being a better type of flow control, but rather torque control. In doing so, they developed a device that balanced the loading of the series motors such that they could experience different flow rates or rotational speeds without cavitation. Enter the HTD 10-40 hydraulic torque divider. The HTD is a pressure control valve designed specifically for this purpose. One can think of the HTD as that magic make-up check valve I previously alluded to earlier in this presentation, one that does allow supplementary flow when required, however, does not place the inlet of the affected motor at low pressure, but rather maintains the pair equally loaded. The HTD is a hybrid type of pressure control valve. Recall, pressure control valves are ordinarily divided into a handful of general categories, namely pressure relief valves, sequence valves, pressure reducing valves, pressure reducing relieving valves, unloading valves, and counterbalance valves, each with their own specific purpose and construction. Pressure control valves, as the name implies, are generally used to monitor and modify pressure in a complete hydraulic circuit or in a specific branch of a larger hydraulic circuit. In these respects, the HTD is most like a pressure-reducing relieving valve in that it maintains pressure in a specific branch of a larger hydraulic circuit at a specified value. The HTD, however, rather than operating at a single static pressure setting, can dynamically respond to changing pressure conditions to ensure that both motors remain equally loaded. In the most basic application of the HTD, the output pressure is half the input pressure, thus ensuring the load remains equally divided between a pair of actuators in a series arrangement, hence the name HTD, hydraulic torque divider. The HTD is a cartridge-style hydraulic pressure-reducing relieving valve, internally piloted to the midpoint of the high-low pressure differential, which may be a dynamically changing quantity. Let's examine the valve symbol. Those familiar with pressure control valves may recognize the HTD as a type of piloted pressure-reducing relieving valve. Port 1 is blocked during normal operation. Port 2 is the supply port. Port 3 is the controlled port, and port 4 is the drain. One end of the spool features a bias spring, and the other end is acted upon by an internal pilot signal referenced at the midpoint of a pressure divider network. As long as the two orifices in the pressure divider network are of equal diameter, the spool will be piloted to half the pressure differential between port 2 supply and port 4 drain. The filter on the pressure divider circuit protects it from contamination. To illustrate basic operation of the HTD necessitates the inclusion of two hydraulic motors in series. We'll examine a more comprehensive application in a moment. The controlled port 3 is connected to the midpoint between the two drive motors. The supply port 2 is connected to pressurized flow from the pump. The drain port 4 is connected to the return or tank. Primary flow through the series circuit can either go left to right or right to left. Let's say primary flow is going left to right and assume this is the forward direction of travel. The HTD is biased to block flow from the supply port 2, yet allow flow from the control port 3 to the drain 4. In this position, the HTD acts as a means of relieving pressure or draining excess flow when motor B is turning slower than motor A. During operation, the internal pilot shifts the spool to allow flow from the supply 2 to the controlled port 3. In this position, the HTD acts as a means of boosting pressure or supplying flow to motor B when motor B is turning faster than motor A. Additionally, this position enables supplemental flow through the HTD to replace any fluid lost through the case drain of motor A. As pressure rises and falls due to load variations, the HTD alternately supplies or relieves flow to or from the controlled port 3 to balance the spool. When the controlled pressure is half the differential between the high and low legs, the spool is balanced. Ultimately, the HTD ensures both motors remain equally loaded despite differences in rotational speed and/or flow rate. You'll find the identical behavior of primary flow through the series arrangement of motors is reversed. Before moving on, it is important to compare and contrast the approach employed by the HTD with our previous makeup check valve approach. Using the HTD, the source of makeup flow is not the tank, but rather the pump. Due to the action of the internal pilot, the pressure of this makeup flow will always be half the total pressure differential in this circuit. Let's examine a more comprehensive application of the HTD to illustrate its behavior. In this scenario, we'll be employing the HTD in a simplified two-wheel hydrostatic drive application. This drive circuit includes a bidirectional variable displacement pump, 2 drive motors in a series arrangement, pressure relief valves to limit the overall pressure in either leg of the circuit, a shuttle or OR valve, and 2 check valves. The HTD assumes a central position. The controlled port 3 is connected to the midpoint between the 2 drive motors. In this circuit, I've drawn the HTD in the balanced condition, allowing it to either relieve or boost pressure to the control port as required. Given this hydrostatic drive circuit is bidirectional in nature, the pair of check valves and shuttle valve resolves which leg is high and which leg is low. When the bidirectional pump operates in the forward direction, supply flow is routed through the shuttle valve to the supply of the HTD, and drain flow from the HTD is routed through the open check valve 2, while check valve 1 remains closed. When the bidirectional pump operates in the reverse direction, supply flow remains routed through the shuttle valve to the supply of the HTD, while drain flow from the HTD is routed through the open check valve 1, while check valve 2 remains closed. Employed in this fashion, the arrangement of the shuttle valve and 2 check valves ensures a continuous connection of the HTD supply and drain ports regardless of the direction of travel. Note, ordinarily the low leg and closed circuit hydrostatic drives is always charged, typically to about 300 psi using a charge pump circuit. This charge replenishes fluid lost to leakage and ensures both the motors and pump operate smoothly and remain lubricated. In order to keep this diagram simplified, I've not included the charging circuit in this diagram. This being said, you should be aware that because the drain port 4 of the HTD is connected to the low circuit leg, rather than the reservoir, the charge pressure would form the baseline reference from which any differential is measured. As previously described, the HTD regulates the pressure between the 2 series motors to a value that is always half the total pressure differential across both. It divides the torque, forcing both motors to equally share the load. During operation, the HTD provides makeup or relieves flow into or out of the circuit to accommodate differences in operating speed between the 2 series motors. In the event the upstream motor experiences leakage, any reduction in flow rate at its outlet would translate to a reduction in pressure at the control port. This occasion would be detected by the HTD, and by shifting into the activated position would allow flow from the supply to the control until pressure again stabilizes at the midpoint. With the HTD keeping the system in balance, the downstream motor does not suffer cavitation as previously. In a true demonstration of the utility of the HTD, whenever the vehicle negotiates a turn, the motors operate at different rotational speeds. Yet the centrally located HTD ensures that the motors remain equally loaded by monitoring pressure at the control port and modulated between the open and closed state. If motor A is in the outside track turning faster than motor B, the HTD diverts a portion of flow, allowing motor B to turn slower, yet remain loaded. If motor B is on the outside track turning faster than motor A, the HTD supplements flow, allowing motor B to turn faster and not only avoid cavitation, but also remain loaded. Instead of freewheeling around the outside track and letting the inside motor do all the work, both motors equally share the load. However, operate at different rotational speeds, a situation ordinarily impermissible by a purely series circuit. In summary, the HTD is that single cost-effective solution that keeps the good and gets rid of the bad. Considering the previously discussed strategies, the HTD implementation presents several clear advantages. Simplicity. The HTD is an all-hydraulic solution, necessitating no expensive electronic sensors nor complicated controllers that require development, programming, or tuning. It operates automatically without the need for operator intervention. The HTD eliminates the need to field tune slip orifices and facilitates easy service and troubleshooting. Cost effectiveness. The HTD is a single component sized to accommodate only the small bypass flow differential between the motors, eliminating the need for an oversized valve. Flow dividers, in contrast, must be sized to accommodate total drive flow. Additionally, the HTD can reduce the weight and size of the oil reservoir and reduce or even eliminate the need for a cooler. Energy savings and efficiency. This change in methodology yields substantial energy savings since flow dividers are notoriously inefficient and can account for a loss of up to 4 to 5 horsepower in a 30 gallon per minute four-wheel drive circuit. These savings can reduce fuel consumption. Performance. Leaking flow dividers or slip orifices can lead to loss of traction. Not so with the HTD. The HTD equally divides torque between the two series motors for traction-critical applications. Note for the previously discussed applications, the pressure divider internal to the HTD features two equally sized orifices, thus creating a control reference signal exactly midway between the high and low legs. This needn't be the case for all applications. The size of the orifices can be varied to achieve alternative ratios. For applications that may have different torque requirements between the front and rear axle, for example, HydraForce offers an HTD with a 75-25 split. Additionally, note that HTD needn't be limited to only two-wheel drive applications. Two HTD valves could be employed to create a simple and effective four-wheel drive application. Let's close out this presentation by reviewing some of the features and benefits of the HTD. As demonstrated, the purpose of the HTD is to divide torque between two series motors. It is sized to accommodate only the turning differential flow. It is a cost-effective, all-hydraulic solution. It saves energy and reduces heat loss compared to traditional flow divider solutions. It features a hardened spool and cage for long life. It is tested to the rigorous standards of the National Fluid Power Association. It is tested at a verification level of 90% and an assurance of 99%. If you're interested in obtaining more information about the HTD 10-40 hydraulic torque divider, or speaking with HydraForce about incorporating the HTD into your design, feel free to visit the HydraForce website at www.hydraforce.com. Power forward with HydraForce.